Yeah, I'm Christopher. This is the presentation, the name of the paper that I'm going to be presenting on. Children are spending more time online than ever before, with 97% of children between 3 and 18 having internet access at home. The problem is that many online spaces, such as social media, don't have strong protective measures, which can expose children to harm, like violence, drugs, and predatory behavior. A 2010 study found that nearly 50% of children have been victims of cyberbullying, and 59% of teens report it experience some sort of abusive online interaction. Existing solutions rely on outdated blacklists, which struggle to keep up with new threats and often block too much or too little content. This research aims to create a safer digital environment for children by using AI to detect and filter content in real time. Our goal is to make the internet a safer place for children without compromising its educational and social benefits. Our solution is Aegis Explorer, a Chrome extension that uses AI to filter harmful content in real time. It uses two AI models, a Bert model for detecting harmful text and a YOLO V8 model for analyzing images. Users can customize filtering settings to block specific categories, which are drugs, explicit gambling, profanity, and games. The extension also provides insightful browsing statistics while respecting the child's privacy. When a user visits a website, the extension extracts the text and images and sends them to the server. Images are instantly removed from the page and are replaced with a gray placeholder with any old text removed as well. The server then processes the data to determine if any content falls into a blocked category, and if flagged, the text is removed, and non-flagged images are added back to the page. This filtering runs continuously as the page updates to allow for real-time filtering. To improve efficiency, the extension tracks flagged content to avoid redundantly querying the server. So here's a demo video that shows the system in action. So first we have a demonstration of how the system processes different types of text and images on a test page. And next, this is the effect on a Google search. This is what it looked like before compared to after. And then this is the extensions configuration interface with the statistics. And these are the customization options for blocking content. Traditional content filtering methods rely on IP-based blocking, which quickly becomes outdated and is ineffective for dynamic websites like social media. And in contrast, AI-based filtering allows for real-time classification as content appears. Unlike many existing solutions that only alert parents after the fact, our system proactively removes inappropriate content before a child sees it. And while many content filtering systems focus on only blocking text or images, our approach handles both. This project trained two AI models, one for text and one for images, to analyze and filter harmful content in real time. For text classification, we use Bert, a transformer-based model that analyzes text in context instead of just flagging specific keywords, which allows for more accurate detection of harmful content. For image classification, we use YOLO V8, an advanced object detection model. Both models were refined through iterative training and dataset improvements. The extension itself is written in HTML, CSS, and JavaScript, while the backend server is written in Python. The server handles classification requests by exposing API routes for the client extension. We did two experiments to evaluate certain aspects of our system. The first experiment focused on evaluating the AI model performance to determine which categories performed well and which struggled. We tested both models on unseen data using the F1 score for text and accuracy for images. So the F1 score is the harmonic mean of the precision and the recall, meaning a high F1 score indicates low false positives and low false negatives. Accuracy measures how often the image model correctly classified content. Since we're only comparing the category performance within each model, we can use different scales for each model. The text model had strong classification performance for categories like explicit content with an F1 score of 89.3 and profanity with 83.4%, but struggled. Image classification model had similar issues with the accuracy dropping below 60% for monetary and social. So this suggested that the data set for those two categories was either too ambiguous or lacked sufficient high quality samples. And since we were unable to obtain better data and these categories were not central to our goals, we decided to exclude them. For the remaining categories, we analyzed the misclassified samples to identify patterns and refine the data accordingly and reran the experiment to assess any improvements. So as shown in these two graphs, there was a clear improvement in the performance of both of the models after refining the dataset, with the image models gambling category reaching 98.2% F1 score, and the text models profanity category reaching 98.4% F1 score. Our second experiment was conducted to determine whether our AI models could process inputs quickly. For our filtering system to be effective, it needs to classify content in real time. If the inference speed is too slow, the system is impractical. So this experiment involves comparing performance on a GPU-powered server against a CPU-only server. We processed 1,000 text inputs using our text model and 1,000 image inputs using our image model. We measured the time it took for each model to classify an input and recorded the result in milliseconds. For the text classification, the GPU machine took 38 milliseconds on average per input, while the CPU machine took 110 milliseconds. For image classification, the GPU processed each image in 42 milliseconds on average, but the CPU took 185 milliseconds. So these findings show that a GPU server is essential for real-time filtering. And we could also explore optimizations like quantizing the models to improve CPU speed or using edge computing to distribute processing across user devices. These experiments revealed a few areas for improvement in our system. So even though our models generally have high accuracy and classification, it's still necessary to expand and refine the data set to reduce the false positives and false negatives. Another issue is our dependency on GPU servers, which increases deployment costs. To address this, we will look into model quantization and distillation techniques, which could help increase speed on CPUs. We also plan to implement client-side optimizations to reduce the amount of data sent to the server and use edge computing to distribute some processing onto user devices. Lastly, our current system classifies text